If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. Imagine the universe as a grand stage, not one of wood and nails, but a vast, invisible framework stretching in every direction. This stage is not static. It bends, stretches, and flexes under the weight of its actors, which include everything from the tiniest particle to the largest galaxy cluster. This is space-time, a concept that revolutionized our understanding of reality and brought us closer to answering questions about the nature of existence itself. To grasp the essence of space-time, one must first set aside the common notion of space as an empty void and time as a ticking clock. Instead, picture them as two interconnected dimensions, seamlessly woven together into a single, fluid entity. This fabric doesn't merely exist, it reacts. Place an object with mass into space-time, and the fabric curves around it, much like a trampoline sags when a heavy ball is placed on it. The heavier the object, the greater the curve. This idea, deceptively simple, forms the cornerstone of our understanding of gravity. Instead of envisioning gravity as a force pulling objects together, think of it as a byproduct of this curvature. A planet orbits a star not because it's being pulled, but because it's following the path carved by the star's distortion of space-time. This realization was the brainchild of Albert Einstein, whose theory of general relativity reshaped the way humanity perceives the universe. At first, the concept of a malleable space-time might seem intangible, even paradoxical. How can something invisible, something we cannot touch or see, dictate the motion of celestial bodies and the passage of time? The key to understanding lies in imagining space-time not as a rigid, static framework, but as a living, dynamic entity. This dynamic nature is why the universe behaves as it does. From the gentle arcs of planetary orbits to the ferocious gravitational pull of black holes. The flexibility of space-time is most evident in the phenomena of gravitational waves. These are ripples in the fabric of space-time, caused by massive objects accelerating through the universe. When two black holes collide, for example, they send waves propagating outward at the speed of light, momentarily stretching and compressing the very structure of the cosmos. These waves, predicted by Einstein and confirmed by modern instruments like LIGO, offer a glimpse into the otherwise invisible dance of space and time. Curiously, space-time isn't merely reactive, it's also predictive. The paths of light, the behavior of matter, and even the flow of time itself are governed by the shape of this fabric. Light traveling near a massive object, like a star or black hole, bends around it in a phenomenon known as gravitational lensing. This bending doesn't occur because light is affected by gravity in the traditional sense, but because the space-time it travels through is curved. This remarkable effect allows astronomers to observe distant galaxies magnified and distorted by the gravitational influence of closer clusters, effectively using the universe itself as a giant lens. Even time, a concept that feels immutable to our daily lives, is subject to the whims of space-time curvature. Near massive objects, time slows down, a phenomenon known as time dilation. For instance, an astronaut orbiting a black hole would experience time at a much slower rate compared to someone far away from such extreme gravitational influence. This isn't science fiction. It's a measurable reality, confirmed by experiments involving highly accurate atomic clocks and satellites. Space-time is not merely a backdrop for the universe's events. It is an active participant. It molds and shapes the universe, while itself being molded and shaped by the energy and mass it contains. This intricate interplay has unlocked answers to questions that once seemed beyond the reach of science. Yet it has also opened new doors of mystery. What, for example, is the true nature of space-time at its smallest scales? Does it break down into discrete units, or does it remain continuous and smooth? These questions lie at the intersection of general relativity and quantum mechanics, two pillars of modern physics that have yet to be fully reconciled. The story of space-time is far from over. With each new observation, from gravitational wave detections to the peculiar motion of galaxies influenced by unseen dark matter, humanity takes another step closer to unraveling the secrets of this cosmic fabric. It is a journey that challenges the limits of imagination and stretches the boundaries of understanding, compelling us to rethink not just the universe, but our place within it. Imagine the universe as a grand stage, not one of wood and nails, but a vast, invisible framework stretching in every direction. This stage is not static. It bends, stretches, and flexes under the weight of its actors, which include everything from the tiniest particle to the largest galaxy cluster. This is space-time, a concept that revolutionized our understanding of reality and brought us closer to answering questions about the nature of existence itself. To grasp the essence of space-time, one must first set aside the common notion of space as an empty void and time as a ticking clock. Instead, picture them as two interconnected dimensions, seamlessly woven together into a single, fluid entity. This fabric doesn't merely exist, it reacts. Place an object with mass into space-time, and the fabric curves around it, much like a trampoline sags when a heavy ball is placed on it. The heavier the object, the greater the curve. This idea, deceptively simple, forms the cornerstone of our understanding of gravity. Instead of envisioning gravity as a force pulling objects together, think of it as a byproduct of this curvature. A planet orbits a star not because it's being pulled, but because it's following the path carved by the star's distortion of space-time. This realization was the brainchild of Albert Einstein, whose theory of general relativity reshaped the way humanity perceives the universe. At first, the concept of a malleable space-time might seem intangible, even paradoxical. How can something invisible, something we cannot touch or see, dictate the motion of celestial bodies and the passage of time? The key to understanding lies in imagining space-time not as a rigid, static framework, but as a living, dynamic entity. This dynamic nature is why the universe behaves as it does. From the gentle arcs of planetary orbits to the ferocious gravitational pull of black holes. The flexibility of space-time is most evident in the phenomena of gravitational waves. These are ripples in the fabric of space-time, caused by massive objects accelerating through the universe. When two black holes collide, for example, they send waves propagating outward at the speed of light, momentarily stretching and compressing the very structure of the cosmos. These waves, predicted by Einstein and confirmed by modern instruments like LIGO, offer a glimpse into the otherwise invisible dance of space and time. Curiously, space-time isn't merely reactive, it's also predictive. The paths of light, the behavior of matter, and even the flow of time itself are governed by the shape of this fabric. Light traveling near a massive object, like a star or black hole, bends around it in a phenomenon known as gravitational lensing. This bending doesn't occur because light is affected by gravity in the traditional sense, but because the space-time it travels through is curved. This remarkable effect allows astronomers to observe distant galaxies magnified and distorted by the gravitational influence of closer clusters, effectively using the universe itself as a giant lens. Even time, a concept that feels immutable to our daily lives, is subject to the whims of space-time curvature. Near massive objects, time slows down, a phenomenon known as time dilation. For instance, an astronaut orbiting a black hole would experience time at a much slower rate compared to someone far away from such extreme gravitational influence. This isn't science fiction. It's a measurable reality, confirmed by experiments involving highly accurate atomic clocks and satellites. Space-time is not merely a backdrop for the universe's events. It is an active participant. It molds and shapes the universe, while itself being molded and shaped by the energy and mass it contains. This intricate interplay has unlocked answers to questions that once seemed beyond the reach of science. Yet it has also opened new doors of mystery. What, for example, is the true nature of space-time at its smallest scales? Does it break down into discrete units, or does it remain continuous and smooth? These questions lie at the intersection of general relativity and quantum mechanics, two pillars of modern physics that have yet to be fully reconciled. The story of space-time is far from over. With each new observation, from gravitational wave detections to the peculiar motion of galaxies influenced by unseen dark matter, humanity takes another step closer to unraveling the secrets of this cosmic fabric. It is a journey that challenges the limits of imagination and stretches the boundaries of understanding, compelling us to rethink not just the universe, but our place within it. As we venture deeper into the mysteries of space-time, the interplay between its curvature and the matter it governs becomes even more fascinating. One of the most profound realizations of modern physics is that the very shape of the universe, the vast, sprawling expanse that encompasses everything, depends on the curvature of space-time. This curvature is not a mere abstract concept. It dictates the structure, behavior, and ultimate fate of the cosmos. To understand this, imagine space-time as a vast, three-dimensional landscape. The universe can take on one of three broad geometries: flat, open, or closed. A flat universe is like an infinite plane, extending endlessly in all directions without curving back on itself. An open universe resembles a saddle, with a curvature that spreads outward indefinitely. A closed universe is akin to the surface of a sphere, finite but unbounded, where traveling far enough in one direction would eventually bring you back to your starting point. Which geometry describes our universe? Observations suggest that we live in a universe that is astonishingly close to flat. This discovery, supported by measurements of the cosmic microwave background radiation, has profound implications for our understanding of the cosmos. A flat universe implies a delicate balance between the gravitational pull of matter and the expansive force of dark energy, a balance so fine that it challenges our intuition about the randomness of cosmic events. The geometry of space-time is shaped by the energy and matter it contains, which includes the mysterious substances known as dark matter and dark energy. These components dominate the universe, with ordinary matter, the kind that forms stars, planets, and humans, making up only a small fraction of the total. Dark matter, though invisible, exerts a gravitational influence that helps bind galaxies together. Without it, the observed motions of stars and galaxies would be inexplicable. Dark energy, on the other hand, acts in opposition to gravity, driving the accelerated expansion of the universe. Its effects are most apparent on the largest scales, where it causes galaxies to drift apart at an ever-increasing rate. This phenomenon raises deep questions about the nature of space-time itself. Is dark energy a property of the vacuum, a manifestation of the inherent flexibility of space-time? Or is it evidence of an entirely new force or field waiting to be discovered? These questions take us to the edge of what we know about space-time and its role in shaping the cosmos. Yet even as we push the boundaries of our understanding, space-time reveals itself in tangible ways closer to home. The bending of light, the slowing of time, and the motion of planets all serve as reminders that we are participants in a vast and interconnected web of phenomena governed by the rules of relativity. Consider the phenomenon of gravitational waves once more. These ripples in the fabric of space-time, produced by catastrophic cosmic events, offer a direct way to listen to the universe. When two black holes merge, the resulting wave propagates outward, carrying information about the masses, spins, and trajectories of the colliding objects. Detecting these waves requires extraordinary precision, as their effects on space-time are incredibly subtle, equivalent to distorting a distance as vast as the Earth's diameter by less than the width of an atom. Yet, despite their faintness, gravitational waves have become a powerful tool for exploring the universe. They provide insights into events that would otherwise remain hidden, such as the collisions of neutron stars or the birth of black holes. These observations confirm Einstein's predictions and open new avenues for understanding the extreme environments where space-time behaves in ways we can scarcely imagine. The interaction between space-time and energy also leads to one of the most intriguing possibilities in physics: the existence of exotic phenomena such as wormholes and cosmic strings. Wormholes, if they exist, would connect distant regions of space-time, creating shortcuts through the universe. While currently speculative, they offer tantalizing possibilities for future exploration and even time travel. Cosmic strings, hypothetical defects in the fabric of space-time, could serve as relics from the early universe, carrying immense energy and potentially offering insights into its origins. This brings us to the beginning of everything, the Big Bang. The birth of the universe was not just the creation of matter and energy, but also the inception of space-time itself. At that singular moment, the entire cosmos was compressed into an unimaginably dense point, where the laws of physics as we know them break down. Space-time emerged and expanded, giving rise to the structure we observe today. This initial state remains one of the greatest mysteries in science, as it challenges our understanding of causality and the nature of time. What existed before the Big Bang? This question is profoundly tied to our understanding of space-time. If time itself began with the Big Bang, then the concept of before loses meaning. Alternatively, some theories propose that our universe is part of a larger multiverse, where space-time as we know it is just one bubble in an infinite sea of possibilities. These ideas, though speculative, push the limits of human imagination and hint at the vast potential for discovery. As we look to the future, the study of space-time promises to revolutionize our understanding of the universe. New technologies, from more sensitive gravitational wave detectors to next-generation telescopes, will allow us to probe deeper into the cosmos and test the limits of relativity. At the same time, the quest to unify general relativity with quantum mechanics, the elusive theory of quantum gravity, offers the potential to unlock a new paradigm of physics. Space-time, in all its complexity and elegance, remains one of the most profound discoveries of human thought. It challenges us to think beyond the confines of our everyday experience and to embrace a universe where time can stretch, space can bend, and the very fabric of reality is alive with motion and possibility. Each new insight deepens our appreciation for the interconnectedness of the cosmos, inspiring a sense of wonder that transcends the boundaries of science and reaches into the realm of the sublime. As we continue our exploration of space-time, we begin to encounter phenomena that stretch the limits of human comprehension. The very fabric of space-time not only reacts to the presence of matter and energy, but also serves as the medium through which some of the universe's most extraordinary processes unfold. These processes, both theoretical and observable, compel us to rethink fundamental concepts about the nature of existence, movement, and reality itself. One of the most fascinating consequences of space-time curvature is the phenomenon of time dilation. Time, which we experience as a constant forward flow, is not universal. It is deeply connected to the curvature of space-time and varies depending on the circumstances. This effect is perhaps most famously illustrated in the thought experiments of special and general relativity. For instance, a person traveling at near light speed or dwelling near a massive object such as a black hole would experience time passing more slowly relative to an observer in a less extreme environment. This isn't just theoretical. Time dilation has been experimentally confirmed and must even be accounted for in technologies like GPS satellites. In the vastness of the cosmos, time dilation becomes a critical factor in understanding high-energy astrophysical events and the potential for human exploration. Imagine astronauts embarking on an interstellar journey near the speed of light. For them, only a few years might pass during the voyage, while decades or even centuries elapse back on Earth. This so-called twin paradox underscores the deep interconnectedness of space and time and serves as a reminder that our perception of reality is relative to our position and movement within space-time. The concept of relativity also has profound implications for the universe's most extreme environments, such as near the event horizon of a black hole. Here, space-time curvature becomes so intense that it dramatically slows the passage of time. To an outside observer, anything approaching the event horizon appears to freeze in time, never quite crossing the boundary. For the object itself, however, time continues normally, but the gravitational forces it experiences grow unimaginably strong, pulling it inexorably toward the singularity. The singularity is a place where our current understanding of physics collapses. At this point, the curvature of space-time becomes infinite, and the known laws of nature cease to apply. What lies beyond a singularity is a question that has puzzled physicists and philosophers alike. Is it a gateway to another universe? A point where space and time are destroyed? Or merely a limitation of our current theories, waiting to be resolved by a future framework that unites general relativity with quantum mechanics? Such questions are not merely academic. They strike at the heart of what it means to exist in a universe governed by space-time. To reconcile the smooth, continuous nature of general relativity with the discrete, probabilistic world of quantum mechanics would be to unlock a new level of understanding about the cosmos. This effort has given rise to some of the most ambitious theories in modern physics, such as string theory and loop quantum gravity, which propose novel ways to describe the structure of space-time at its smallest scales. At these quantum scales, space-time may not be the smooth continuum we observe on macroscopic levels, but instead resemble a frothy, turbulent quantum foam. In this view, space-time fluctuates wildly at tiny distances, with particles and energy appearing and disappearing in fleeting moments. These fluctuations could provide the key to understanding the fabric of reality and may even hold answers to questions about the origins of the universe. As we consider these microscopic details, it's worth reflecting on how they connect to the grander scales of the cosmos. Space-time is not static. It is expanding, driven by the mysterious force of dark energy. This expansion is not merely the motion of galaxies moving apart, but the stretching of space-time itself. This means that the very distance between objects in the universe is growing, a process that will eventually push some galaxies beyond our observable horizon. This brings us to the concept of the cosmic horizon, the boundary beyond which we can no longer observe or receive information. As the universe expands, this horizon shifts, gradually swallowing distant galaxies as their light is stretched into wavelengths too long to detect. This effect has profound implications for our understanding of the universe's size and structure. If space-time continues to expand indefinitely, vast regions of the cosmos may become forever inaccessible to observation, leaving future generations with a smaller, dimmer picture of the universe. Despite these limitations, humanity's ability to probe space-time continues to grow. The detection of gravitational waves, for example, has opened a new window into the cosmos, allowing us to observe events that would otherwise be invisible. These ripples in space-time carry information about their sources, such as merging black holes or neutron stars, and offer a unique way to study the most violent and energetic processes in the universe. Beyond observational advances, theoretical physics pushes us toward even more speculative ideas, such as the nature of wormholes. If space-time can be curved to form tunnels connecting distant regions, could these structures be traversable? While current understanding suggests that wormholes would collapse under their own gravity or require exotic matter to remain stable, the possibility fuels imaginations about the future of space travel. Such shortcuts through space-time could revolutionize our ability to explore the cosmos, enabling journeys across vast distances in a fraction of the time. Even more intriguing is the idea of manipulating space-time itself. Advanced civilizations, if they exist, might have the capability to harness space-time curvature for practical purposes. Could gravity be engineered to create energy? Could space-time be bent to shield planets from cosmic threats? These concepts remain speculative, but underscore the untapped potential of space-time as both a tool and a frontier for exploration. As we consider the future of space-time research, one thing becomes clear: its study is a journey without end. Each new discovery leads to more questions, more possibilities, and more wonder. Space-time is not merely a framework for understanding the universe. It is the key to unlocking its deepest secrets. And as we strive to comprehend this enigmatic fabric, we are reminded of the boundless creativity of the cosmos and the infinite potential of human curiosity. The journey through the mysteries of space-time continues to challenge our understanding of reality, leading us to concepts that stretch the boundaries of what is scientifically conceivable. As we explore, we begin to recognize space-time as not merely a backdrop for the events of the universe, but an active participant in its dynamics. Every particle, every force, and every phenomenon interacts with space-time in a dance that defines the very nature of existence. One of the most intriguing aspects of this interaction is the phenomenon of gravitational lensing. When light passes near a massive object, such as a galaxy or a black hole, the curvature of space-time bends its path, much like a lens bends light in a telescope. This effect not only allows us to observe distant celestial objects magnified or distorted, but also provides a unique way to map the invisible. Dark matter, for instance, reveals itself through the gravitational lensing effects it causes, despite being otherwise undetectable. The ability to use gravitational lensing as a cosmic magnifying glass has led to extraordinary discoveries. Astronomers have identified galaxies so distant that their light has traveled for billions of years to reach us, stretched and bent by the intervening spacetime. These observations provide a glimpse into the early universe, allowing us to study its formation and evolution. Gravitational lensing has even been used to detect exoplanets, revealing the presence of planets orbiting stars light years away by analyzing the subtle distortions in light caused by their gravitational influence. At the other extreme of the universe's scale, the study of black holes continues to push our understanding of space-time to its limits. Black holes are not just objects of immense mass. They are regions where space-time curvature becomes so extreme that conventional physics breaks down. The event horizon marks the boundary where nothing, not even light, can escape, making black holes the ultimate manifestation of gravity's power. Recently, advances in technology have enabled us to directly observe black holes for the first time. The Event Horizon Telescope captured an image of the supermassive black hole at the center of the galaxy M87, revealing a glowing ring of light encircling a shadow, the silhouette of the event horizon. This achievement not only confirmed predictions of general relativity, but also demonstrated the interconnectedness of space-time with light and matter. Yet, black holes are not merely cosmic endpoints. They also challenge our understanding of information in the universe. The information paradox arises from the apparent conflict between quantum mechanics and general relativity regarding what happens to information that falls into a black hole. Quantum theory suggests that information cannot be destroyed, yet black holes appear to obliterate everything that crosses the event horizon. Resolving this paradox could revolutionize our understanding of space-time and its relationship to the quantum realm. Beyond black holes, the fabric of space-time plays a central role in shaping the large-scale structure of the universe. Galaxies and galaxy clusters form along massive filaments of matter that stretch across the cosmos, creating a vast cosmic web. This structure is a direct consequence of the interplay between space-time curvature and the gravitational forces exerted by matter. Understanding how this web came to be and how it evolves requires us to consider not only the visible matter within the universe, but also the dark matter and dark energy that govern its expansion and behavior. Dark energy, in particular, represents one of the greatest mysteries in cosmology. Its discovery, based on observations of distant supernovae, revealed that the universe's expansion is accelerating, rather than slowing down as previously expected. This acceleration implies the presence of a force that counteracts gravity on the largest scales, stretching space-time itself. While its nature remains unknown, dark energy constitutes a significant portion of the universe's total energy density, profoundly influencing its ultimate fate. The interplay between space-time and these unseen forces has led to numerous speculative theories. Could dark energy be a manifestation of a deeper property of space-time, such as the energy of the vacuum itself? Or might it be evidence of a new particle or field waiting to be discovered? These questions lie at the cutting edge of modern physics and require us to think beyond traditional models of the universe. One particularly fascinating concept is the idea that space-time may not be the smooth, continuous fabric described by general relativity. Instead, at the smallest scales, it could be discrete, composed of tiny quanta or loops. This idea, central to theories like loop quantum gravity, suggests that space-time itself has a granular structure, much like matter is composed of atoms. If true, this would fundamentally alter our understanding of the universe's geometry and dynamics. Exploring the quantum nature of space-time could also shed light on the early moments of the universe. During the Big Bang, the entire cosmos was compressed into an unimaginably dense and hot state where quantum effects dominated. Understanding how space-time behaved in this primordial state could reveal clues about the origins of the universe and the mechanisms that drove its rapid expansion. The study of space-time is not confined to theoretical physics or distant galaxies. It also has profound implications for the future of humanity. As our understanding of space-time deepens, so too does our ability to harness it for practical purposes. Technologies that manipulate gravity, light, or even time could revolutionize transportation, communication, and energy production. Concepts like warp drives, which exploit the curvature of space-time to achieve faster-than-light travel, remain speculative but illustrate the transformative potential of this field. Ultimately, space-time is a reminder of the profound interconnectedness of the universe. It ties together the largest structures and the smallest particles, the past and the future, the known and the unknown. As we continue to unravel its secrets, we are not just learning about the cosmos. We are learning about ourselves, our place in the vastness of existence, and our capacity to understand the deepest truths of reality. As we delve even further into the mysteries of space-time, we uncover questions that redefine the boundaries of scientific inquiry and human imagination. Space-time is not merely the stage for the cosmic drama. It is the dynamic and malleable entity that shapes and is shaped by everything within the universe. From the motion of galaxies to the dance of subatomic particles, space-time governs the rules, yet it also hints at a reality far deeper than we currently comprehend. One of the most intriguing frontiers in the study of space-time lies at the intersection of general relativity and quantum mechanics. These two foundational pillars of physics describe reality in ways that are fundamentally different, yet they must coexist in a universe governed by both the immense and the infinitesimal. General relativity provides a stunningly accurate description of how massive objects warp space-time, while quantum mechanics excels in explaining the behavior of particles and forces at the smallest scales. However, their mathematical frameworks are notoriously incompatible, particularly in environments of extreme curvature, such as the interiors of black holes or the earliest moments of the Big Bang. This conflict has led to decades of efforts to develop a theory of quantum gravity, which would unify these two seemingly disparate domains. Among the most prominent contenders is string theory, which proposes that the fundamental building blocks of the universe are not particles but tiny, vibrating strings of energy. These strings, in their various modes of vibration, give rise to the particles and forces we observe, and their interactions are embedded in a higher dimensional space-time. String theory suggests that the apparent incompatibility between general relativity and quantum mechanics may arise because our understanding of space-time is incomplete, limited by our inability to perceive its true multidimensional nature. In addition to string theory, approaches like loop quantum gravity offer alternative insights into the fabric of space-time. This theory envisions space-time as composed of discrete, finite loops woven together into a granular structure. If proven correct, this idea would upend the traditional view of space-time as a smooth continuum, replacing it with a dynamic network that evolves at the Planck scale, the smallest measurable unit of the universe. The implications of these theories extend far beyond theoretical physics. A quantum understanding of space-time could provide answers to some of the universe's most enduring mysteries, such as the nature of singularities. Within a black hole, for instance, classical physics predicts an infinite density and curvature, yet quantum gravity might reveal a resolution to this paradox, showing that the singularity is not a point of infinite values, but a region governed by as yet unknown quantum rules. This quest for understanding also opens the door to exploring what came before the Big Bang. If time itself began with the Big Bang, then concepts like before may not apply in the traditional sense. However, certain theories suggest that our universe could be part of a larger multiverse, where countless other space-time bubbles exist, each with its own unique properties. In this context, the Big Bang might represent the birth of our particular bubble within a vast cosmic landscape, with other universes forming, evolving, and perhaps even interacting with ours. Such speculative ideas raise profound philosophical questions. What does it mean for something to exist outside of our space-time? If other universes operate under different physical laws, can we ever truly understand them? Or are we forever confined to the limits of our own cosmic bubble? These questions remind us that the study of space-time is as much about confronting the unknown as it is about expanding the boundaries of the known. On more practical scales, our deepening understanding of space-time continues to transform how we explore and interact with the cosmos. Advances in gravitational wave astronomy, for example, allow us to probe regions of the universe that were previously inaccessible. These ripples in space-time provide information not only about the events that generated them, such as merging black holes, but also about the fabric of space-time itself. By studying these waves, scientists hope to uncover new insights into the fundamental properties of the universe, from its expansion rate to the distribution of dark matter. Moreover, the concept of space-time manipulation continues to inspire visions of future technologies. While the idea of faster-than-light travel remains speculative, certain theoretical models suggest that space-time could be warped in ways that enable rapid traversal of vast distances. The so-called Alcubierre drive, for instance, envisions creating a bubble of space-time that contracts ahead of a spacecraft and expands behind it, effectively allowing the craft to move faster than light without violating relativity. While such concepts face enormous practical and energy-related challenges, they highlight the transformative potential of space-time physics. Even more immediately, our understanding of space-time plays a crucial role in the technologies we rely on every day. From GPS systems to telecommunications, the precision with which we navigate and communicate depends on accounting for the effects of relativity. Satellites, for example, operate in weaker gravitational fields than those on Earth's surface, causing their clocks to run slightly faster. Engineers must account for this discrepancy to ensure accuracy, demonstrating how the curvature of space-time has tangible impacts on our lives. As humanity looks toward the stars, the insights gained from studying space-time will be essential for future exploration. Understanding how time and space behave near massive objects, for instance, could help us design missions to distant planets or moons, where gravitational conditions differ significantly from those on Earth. Furthermore, advances in space-time physics may one day enable humanity to establish outposts beyond our solar system, ensuring our survival and opening new frontiers for discovery. The study of space-time also reminds us of the profound interconnectedness of the cosmos. Every particle, every wave, and every phenomenon contributes to the dynamic tapestry of the universe. Space-time is not merely a backdrop, but an integral part of the story, linking the smallest quanta to the largest structures, the fleeting moment to the vast expanse of eternity. As we strive to unravel its mysteries, we are not just seeking knowledge about the cosmos. We are also seeking a deeper understanding of ourselves. The questions we ask about space-time reflect our innate curiosity and our drive to explore, to learn, and to connect with the universe that gave us life. With each discovery, we take another step on this journey, guided by the boundless potential of human imagination and the infinite complexity of the cosmos. The profound exploration of space-time inevitably leads us to consider not just its structure and behavior, but also its implications for the grandest questions of existence. As a dynamic, malleable entity, space-time serves as the foundation upon which all physical phenomena unfold. Its properties govern the motion of stars, the collapse of black holes, and even the flow of time itself. Yet the more we uncover, the more we realize how much remains hidden, waiting for discovery. One of the most compelling aspects of space-time is its role in shaping the ultimate destiny of the universe. The expansion of the cosmos, driven by the mysterious force of dark energy, suggests that the fabric of space-time is not static but evolving. Current observations indicate that the rate of expansion is accelerating, a phenomenon with profound implications for the future. If this acceleration continues indefinitely, the universe may end in a big freeze, where galaxies drift so far apart that stars exhaust their fuel, leaving behind a cold, dark, and lifeless expanse. Alternatively, dark energy could evolve in ways we do not yet understand. If it strengthens over time, it might lead to a big rip, tearing apart not just galaxies and stars, but even atoms and the very fabric of space-time itself. Conversely, if dark energy diminishes, the expansion of the universe could slow and reverse, culminating in a big crunch where all matter and energy collapse into a singularity, echoing the conditions of the Big Bang. These scenarios are deeply tied to the geometry and dynamics of space-time. A universe with positive curvature, akin to the surface of a sphere, might eventually collapse, while a flat or negatively curved universe could expand forever. Determining the precise geometry requires precise measurements of cosmic parameters, such as the density of matter and the behavior of dark energy. Each observation brings us closer to answering these cosmic questions, yet also introduces new layers of mystery. The nature of time within space-time raises equally profound questions. In our everyday experience, time appears to flow in a single direction, from past to future. This arrow of time is deeply tied to the second law of thermodynamics, which states that entropy, the measure of disorder in a system, tends to increase over time. Yet, on a fundamental level, the equations of physics are time-symmetric, meaning they work equally well in reverse. This discrepancy has led physicists to explore whether the arrow of time is an emergent property of spacetime's large-scale structure, rather than an inherent feature of the universe. One speculative idea is that time itself might be an illusion, a construct arising from our limited perception of spacetime. In this view, past, present, and future coexist in a block universe, where time is just another dimension like space. Such concepts challenge our most basic intuitions and invite us to rethink the nature of reality itself. The study of space-time also forces us to confront the limits of observation and knowledge. The observable universe, the portion of the cosmos we can see and study, is bounded by the speed of light and the age of the universe. As space-time expands, distant galaxies recede beyond our ability to detect them, effectively erasing parts of the cosmos from view. This growing observational horizon raises questions about the completeness of our understanding. Are we observing a representative sample of the universe, or is our perspective inherently limited by our position in spacetime? Beyond the observable universe lies the tantalizing possibility of the multiverse, a collection of universes, each with its own space-time and physical laws. If true, the multiverse could explain why our universe has the properties it does, such as the fine-tuned constants that allow for the existence of life. Yet the multiverse hypothesis also challenges traditional notions of science, as many of these parallel universes may be forever beyond the reach of observation or experiment. Closer to home, space-time plays a pivotal role in our efforts to explore and colonize the cosmos. Human space travel, limited as it currently is, involves navigating the complexities of space-time on practical scales. Missions to the Moon, Mars, or beyond must account for gravitational effects, orbital dynamics, and relativistic time dilation. As we expand our reach, understanding the nuances of space-time will become increasingly important, particularly for long-duration missions where the passage of time for astronauts might differ significantly from that on Earth. The possibility of manipulating space-time for advanced propulsion systems or energy generation also fuels the imagination. Concepts like warp drives, while purely theoretical at present, are rooted in the equations of general relativity. By bending or folding space-time, such technologies could enable faster-than-light travel without violating the known laws of physics. However, the immense energy requirements and the need for exotic matter, substances with negative energy density, remain significant obstacles. Even without such breakthroughs, the exploration of space-time continues to yield practical benefits. Gravitational wave astronomy, for instance, has provided a new way to study the universe, complementing traditional observations of light and particles. By detecting the ripples in space-time caused by cataclysmic events like black hole mergers, scientists gain insights into phenomena that were previously inaccessible. These observations not only confirm Einstein's predictions, but also open the door to discoveries that could redefine our understanding of the cosmos. The pursuit of knowledge about space-time is also deeply human, reflecting our innate curiosity and our drive to understand the universe and our place within it. Each new insight deepens our appreciation for the interconnectedness of the cosmos, revealing a reality that is both elegant and complex. Space-time is not just a concept for physicists and astronomers. It is the very fabric of existence, touching every aspect of life and thought. As we continue to explore, we are reminded of the words of Albert Einstein, who described the pursuit of science as the refinement of everyday thinking. Space-time, with its profound mysteries and endless possibilities, challenges us to refine our understanding not just of the universe, but of ourselves. It invites us to look beyond the immediate and the familiar, to embrace the vastness of the unknown, and to marvel at the boundless creativity of the cosmos. The exploration of space-time brings us face to face with concepts so profound and intricate that they border on the philosophical. At its core, space-time is a framework, yet it is also an active participant in the cosmic story. It is both the stage upon which the universe unfolds and a dynamic entity shaped by the events it hosts. As we probe deeper, the distinctions between space, time, and matter begin to blur, revealing a reality that is interconnected in ways we are only beginning to grasp. One of the most profound consequences of spacetime's nature is its influence on causality, the relationship between cause and effect. In our everyday lives, causality feels intuitive and absolute. Actions lead to consequences, and the flow of time ensures events unfold in a logical sequence. However, in the relativistic framework of spacetime, causality becomes more flexible. Events that appear simultaneous to one observer may occur in different orders for another, depending on their relative motion. This relativity of simultaneity challenges our intuitive notions of time and underscores the profound interconnectedness of space-time and perception. This flexibility raises fascinating questions about the possibility of time travel. In theory, certain configurations of space-time could create closed time-like curves, paths that loop back on themselves, allowing an object to return to its own past. Such scenarios are mathematically permissible in Einstein's equations, but they remain purely theoretical due to the practical and paradoxical challenges they present. For instance, the grandfather paradox asks what would happen if a time traveler prevented their own existence by altering the past. Resolving such paradoxes may require a deeper understanding of space-time, quantum mechanics, or even entirely new physics. The potential for time travel is closely tied to the concept of wormholes. These hypothetical structures, also known as Einstein-Rosen bridges, are shortcuts through space-time that could connect distant regions of the universe. While current understanding suggests that wormholes would collapse too quickly to allow passage, their existence cannot yet be ruled out. If stable wormholes could be created or discovered, they would revolutionize our understanding of space-time and open unprecedented possibilities for exploration and communication. Beyond these speculative ideas, the study of space-time continues to yield practical insights that impact our daily lives. Technologies like GPS, which rely on precise timing and positioning, must account for the effects of general and special relativity. Satellites orbiting Earth experience weaker gravitational fields and move at high velocities, causing their clocks to run faster than those on the surface. Without corrections for these relativistic effects, GPS systems would quickly become inaccurate, highlighting how deeply our modern world is tied to the properties of space-time. As we extend our reach into the cosmos, our understanding of space-time will play an even greater role in shaping the future of space exploration. Missions to distant planets, moons, or even other star systems will require precise navigation through the curved geometry of space-time. Time dilation, gravitational effects, and relativistic speeds will need to be accounted for to ensure the success and safety of such missions. For instance, astronauts traveling at high speeds or near massive objects may experience significant differences in the passage of time relative to observers on Earth, complicating communication and coordination. The potential for manipulating space-time also fuels speculation about the far future of human technology. Concepts like the Alcubierre drive, which proposes faster-than-light travel by contracting space-time ahead of a spacecraft and expanding it behind, remain theoretical but tantalizing. Such a mechanism would require enormous amounts of energy and possibly exotic matter with negative energy density, challenges that place it firmly in the realm of speculation. However, the very fact that such ideas are mathematically conceivable underscores the transformative potential of space-time physics. On the largest scales, space-time continues to shape our understanding of the universe's structure and behavior. The cosmic web, a vast network of galaxies and dark matter, reflects the influence of space-time's curvature on the distribution of matter. Observations of this structure provide critical insights into the universe's history, from its earliest moments to its current state. The discovery of dark energy, which drives the accelerated expansion of space-time, has added another layer of complexity to this picture, raising questions about the universe's ultimate fate. One of the most exciting developments in recent years has been the rise of gravitational wave astronomy. These ripples in space-time, caused by massive objects like merging black holes, offer a new way to study the cosmos. Unlike light or particles, gravitational waves travel virtually unimpeded through space-time, carrying information about their sources and the environments in which they were generated. By detecting and analyzing these waves, scientists can explore phenomena that were previously inaccessible, such as the formation of black holes, the properties of neutron stars, and even the behavior of space-time itself. The study of gravitational waves also connects us to the earliest moments of the universe. Certain theories suggest that primordial gravitational waves, generated during the inflationary period shortly after the Big Bang, could carry information about the universe's birth. Detecting these waves would provide direct evidence of inflation and offer unprecedented insights into the origins of space-time and the physical laws that govern it. As we continue to explore these frontiers, we are reminded of the profound interconnectedness of the cosmos. Space-time is not an isolated phenomenon. It is deeply tied to the forces, particles, and structures that make up the universe. Its behavior reflects the influence of gravity, electromagnetism, and even quantum mechanics, creating a unified tapestry that spans the largest and smallest scales. Understanding this interconnectedness is key to answering some of the most profound questions in science, from the nature of dark matter and dark energy to the ultimate fate of the universe. Space-time also challenges us to think beyond the limitations of our current knowledge. Theories that attempt to unify general relativity and quantum mechanics, such as string theory and loop quantum gravity, suggest that our understanding of space-time may be incomplete. These theories propose that space-time itself could be composed of discrete units or higher dimensional structures, hinting at a deeper layer of reality waiting to be uncovered. Ultimately, the study of space-time is not just about understanding the universe, it is about understanding our place within it. The questions we ask about space-time reflect our innate curiosity and our drive to explore, to learn, and to connect with the cosmos. As we uncover its secrets, we are reminded of the boundless potential of human imagination and the infinite complexity of the universe. As we journey further into the intricate depths of space-time, the boundaries between science, philosophy, and imagination blur ever more profoundly. Space-time, at its essence, is the fabric of the universe. Yet it is also the key to understanding phenomena that stretch the limits of human comprehension. Its role as both a medium and an active participant in the cosmos challenges us to reconsider what we know about reality itself. One of the most perplexing aspects of space-time lies in its relationship with energy and mass, as described by Einstein's famous equation, E equals mc2 E equals mc caret 2 E equals mc2. This equation demonstrates that energy and mass are interchangeable, meaning that both have the capacity to warp space-time. A star bends the space-time around it through its immense mass, while a high-energy particle moving at near-light speed also exerts an influence, albeit on a much smaller scale. This interplay reveals the profound symmetry at the heart of the universe, where mass, energy, and space-time are inextricably linked. The warping of space-time is most evident in extreme environments, such as the vicinity of black holes. These objects, formed from the collapse of massive stars, represent regions where space-time is curved to its breaking point. The immense gravitational pull of a black hole is not just a consequence of its mass, but also of the way it bends the surrounding space-time. Near the event horizon, this curvature becomes so extreme that it traps everything within, including light. To an external observer, time appears to slow to a standstill at the event horizon, a phenomenon that highlights the intimate connection between space, time, and gravity. Yet black holes are not just cosmic vacuum cleaners. They are engines of transformation. Matter that falls into a black hole releases enormous amounts of energy as it accelerates and heats up, creating jets of radiation that can be observed across vast distances. These high-energy emissions, known as quasars, are among the brightest objects in the universe and offer a glimpse into the violent processes occurring at the edges of space-time's most extreme distortions. Black holes also challenge our understanding of information and entropy. The information paradox arises from the apparent loss of information about the matter that falls into a black hole. According to quantum mechanics, information cannot be destroyed, yet black holes seem to obliterate it entirely. This paradox has spurred some of the most groundbreaking theoretical work in modern physics, including the idea that information might be preserved in the two-dimensional surface of the event horizon, encoded in a holographic manner. This concept of a holographic universe extends beyond black holes. Some theories propose that all of space-time might be a three-dimensional projection of information encoded on a two-dimensional surface, much like a hologram. If true, this idea would fundamentally alter our understanding of the universe, suggesting that space-time itself is not as it seems, but is instead an emergent property arising from deeper principles. These speculative theories intersect with the quest to understand the quantum nature of space-time. At the smallest scales, the smooth fabric described by general relativity gives way to a chaotic, turbulent landscape known as quantum foam. This seething sea of uncertainty, where particles and energy fluctuate wildly, defies classical descriptions of space-time and suggests that its structure may be fundamentally discrete rather than continuous. Exploring this quantum realm could reveal the building blocks of reality and unlock new avenues for unifying physics. The implications of such discoveries are staggering. A quantum theory of gravity could resolve long-standing mysteries about the origins of the universe, the nature of singularities, and the fundamental limits of observation. It might also pave the way for technologies that harness the properties of space-time itself, from advanced propulsion systems to methods of energy generation that tap into the underlying structure of reality. The study of space-time also raises questions about its boundaries. Is space-time infinite, or does it have an edge? If it does, what lies beyond? These questions challenge the very definition of existence. In a multiverse scenario, our space-time might be one of countless bubbles within a larger cosmic landscape, each governed by its own set of physical laws. This perspective shifts the focus from understanding a single universe to exploring the principles that allow for the existence of multiple, diverse realities. Closer to home, space-time continues to shape our understanding of the observable universe. The discovery of dark energy, which accelerates the expansion of space-time, has revolutionized cosmology. This mysterious force dominates the energy density of the universe and influences its ultimate fate. Yet its nature remains elusive. Is dark energy a fundamental property of space-time itself? Or does it hint at new particles or forces that have yet to be discovered? Answering this question could reveal insights into the deepest workings of the cosmos. The expansion of space-time also affects our ability to observe the universe. As galaxies move farther away, their light is stretched into longer wavelengths, a phenomenon known as redshift. Eventually, some galaxies will move so far beyond our observational horizon that their light will never reach us, effectively erasing them from the visible universe. This ever-shrinking observable cosmos reminds us of the transient nature of knowledge and the importance of studying space-time while we can. The profound interconnectedness of space-time and matter also manifests in phenomena such as gravitational waves. These ripples, generated by events like black hole mergers or neutron star collisions, propagate through space-time, carrying information about their sources. The detection of these waves has opened a new window into the universe, allowing us to study events that were previously invisible. As gravitational wave detectors become more sensitive, they promise to unveil even more secrets about the cosmos, from the properties of compact objects to the conditions of the early universe. Ultimately, the study of space-time is a journey of discovery that reflects humanity's deepest aspirations. It challenges us to think beyond the immediate and the familiar, to confront questions about the nature of existence, and to embrace the boundless complexity of the cosmos. Space-time is not just a scientific concept. It is a testament to the power of human curiosity and the infinite potential of exploration. The deeper we venture into the mysteries of space-time, the more its interconnectedness with the universe reveals itself as a tapestry woven from threads of gravity, energy, and quantum phenomena. It becomes increasingly clear that space-time is not merely a passive arena, but an active and dynamic entity that responds to, and even governs, the cosmic dance of matter and energy. Each discovery adds a layer of complexity and wonder to our understanding, compelling us to rethink not only the cosmos but our place within it. One of the most extraordinary revelations about space-time is its role in shaping the large-scale structure of the universe. From the smallest subatomic particles to the largest galaxy clusters, everything exists and interacts within the framework of this four-dimensional fabric. Space-time, though intangible to our senses, is the scaffold that supports the cosmic web, a vast network of galaxies and dark matter filaments stretching across the observable universe. This structure, formed over billions of years, is a direct result of space-time's response to the distribution of matter and energy. The cosmic web is not merely a static formation. It is a dynamic entity, constantly evolving as galaxies merge, collide, and drift apart. Gravity, the curvature of space-time caused by mass, is the force driving this evolution. Dark matter, an invisible substance that constitutes much of the universe's mass, exerts gravitational influence that helps bind galaxies together and shapes the web's intricate filaments. Without dark matter, the visible structures of the cosmos could not have formed in their current configuration. Yet dark matter itself is an enigma. It does not emit, absorb, or reflect light, making it undetectable through conventional means. Its presence is inferred solely through its gravitational effects, which warp space-time and influence the motion of stars and galaxies. The nature of dark matter remains one of the greatest unsolved mysteries in astrophysics. Is it composed of undiscovered particles, or does it point to a deeper modification of our understanding of gravity and space-time? Each possibility carries profound implications for the nature of the cosmos. Beyond dark matter lies the even greater mystery of dark energy. This enigmatic force, first discovered through observations of distant supernovae, is driving the accelerated expansion of the universe. Dark energy appears to act as a repulsive force, counteracting the pull of gravity and stretching space-time itself. While it constitutes approximately 70% of the universe's total energy density, its nature remains elusive. Is it a property of the vacuum of space-time, or does it arise from an unknown field or particle? Understanding dark energy is essential to determining the ultimate fate of the universe. The interplay between space-time and dark energy raises profound questions about the geometry and dynamics of the cosmos. Observations suggest that the universe is remarkably flat, meaning its overall curvature is close to zero. This flatness implies a delicate balance between the energy driving the expansion of space-time and the matter that curves it inward. The precise tuning required for this balance challenges our understanding of cosmic evolution and has led to theories about inflation, a rapid expansion of space-time that occurred in the moments after the Big Bang. Inflation, if confirmed, would explain not only the flatness of the universe, but also its large-scale uniformity and the distribution of cosmic structures. During this brief but intense period, space-time expanded exponentially, smoothing out irregularities and stretching quantum fluctuations into the seeds of galaxies. These fluctuations, preserved as tiny variations in the cosmic microwave background radiation, provide a window into the early universe and the processes that shaped its evolution. The study of spacetime's expansion also connects us to one of the most intriguing aspects of cosmology, the cosmic horizon. As the universe expands, the observable region of spacetime grows smaller relative to its total size. Distant galaxies recede faster than their light can travel to us, effectively disappearing from view. This loss of observable information poses a challenge to our understanding of the universe's full scope and reminds us of the transient nature of our knowledge. Despite these limitations, humanity has made extraordinary progress in probing the depths of spacetime. Gravitational wave astronomy has emerged as a groundbreaking tool, allowing us to study phenomena that were previously invisible. The detection of these waves, caused by cataclysmic events like black hole mergers, provides a new way to explore the cosmos and test the limits of general relativity. As detectors become more sensitive, they promise to reveal even more about the universe's most extreme environments. On smaller scales, Spacetime's interplay with quantum mechanics continues to challenge and inspire. The quest to reconcile general relativity with quantum theory has led to some of the most ambitious and speculative ideas in physics, including string theory and loop quantum gravity. These theories propose that spacetime itself may have a granular structure, composed of tiny, discrete units or loops. If true, this would fundamentally alter our understanding of the universe's fabric and open new avenues for exploration. One particularly intriguing implication of quantum spacetime is the possibility of a foam-like structure at the Planck scale, where fluctuations become so intense that classical descriptions of spacetime break down. This quantum foam could hold the key to understanding the origins of the universe, the behavior of singularities, and even the nature of time itself. It may also provide insights into the fundamental constants of nature and why they take the values they do. The pursuit of these questions is not only a scientific endeavor, but also a profoundly human one. Spacetime, in all its complexity and elegance, reflects our deepest aspirations to understand the universe and our place within it. Each new discovery brings us closer to unraveling the mysteries of existence, while also reminding us of the vastness of what remains unknown. The study of spacetime challenges us to think beyond the confines of our everyday experience, to embrace the infinite possibilities of the cosmos, and to confront questions that touch the very essence of reality. It is a journey without end, driven by curiosity, imagination, and the unyielding desire to explore the uncharted realms of the universe. If you liked the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.